two suns rising over the same horizon. For most of human history, that existed only in imagination. But what if I told you we've found a world where this happens every single day, and it's closer to us than any planet like it we've ever discovered? Stay with me for the next several minutes because we're about to journey to one of the most extraordinary places humanity has ever detected. We're going to explore a planet that challenges everything we thought we knew about how worlds can exist, how they form, and what's actually possible in this vast universe of ours. We'll uncover why this discovery matters not just to astronomers in their observatories, but to anyone who's ever looked up at the night sky and wondered what else is out there. We'll dive into the strange physics that keeps this world alive between two stars, the remarkable detective work that revealed its existence, and what it tells us about the billions of other worlds hiding in the darkness beyond our solar system. You see, this isn't just another exoplanet discovery. This is a world that shouldn't exist according to the rules we spent decades establishing. A planet threading a gravitational needle so precise that one wrong move would send it spiraling into oblivion. And yet there it is, orbiting steadily, defying our expectations, rewriting our textbooks. If that fascinates you, if the idea of twin sunrises on alien worlds makes you want to understand more about what's really out there, do me a favor right now. Hit that like button, subscribe to this journey we're taking together into the cosmos, and drop a comment telling me, have you ever wondered what it would be like to stand under two suns instead of one? Because now we're not just wondering anymore, we're discovering. Let me take you there. Picture an alien sky painted in colours Earth has never seen. One sun glows fierce and bright, pouring yellow-white light across the landscape. The other burns cooler, deeper, casting shadows the colour of old embers. Together they climb into a sky that operates by rules completely foreign to everything we know. If this sounds like something from Star Wars, you're not wrong. This is real-life Tatooine. This is happening right now on a world we call HD Hersunting 3811 ABB, and it's forcing us to rethink what we understand about planetary systems, about where planets can exist, about the sheer diversity of environments the universe can create. The name itself, HD 3811 ABB, sounds like something from a catalogue of the future, doesn't it? A designation that might appear in some starfaring civilization's database. But every part of that name tells a story. HD 143811 refers to the star system, two stars locked in an eternal gravitational embrace, spinning around each other in a cosmic dance that's been going on for billions of years. The AB tells us we're dealing with a binary system, two stars instead of one. And that lowercase b at the end, that's the planet, the world that circles both of them, caught between two sources of gravity so massive that the slightest miscalculation in its orbit would mean destruction. This system is a member of the Scorpius-Centaurus Association, the closest star-forming region to our solar system, and for years it was just another binary star system among countless others scattered across our galaxy. Astronomers catalogued it, noted it, moved on. Nothing particularly special. Two stars doing what binary stars do, orbiting their shared centre of mass, burning their fuel, existing in the quiet darkness of space. But in 2016, the Gemini Planet Imager first captured images of something extraordinary hiding in that system, a faint point of light that would later be confirmed as a planet. The discovery lay hidden in the data for years until December 2025, when independent teams from Northwestern University and the University of Exeter analysed archival observations and cross-verified them with new Keck observatory data, something that changed everything. Advanced direct imaging using these telescopes captured actual light from the planet itself. The telltale signatures that scientists have learned to recognise as evidence of something profound. When they analysed the numbers, confirmed and reconfirmed what they were seeing, they realised they'd discovered a planet not orbiting one of those stars, orbiting both. We call these circumbinary planets, and the term barely captures what they represent. These are worlds caught in gravitational ballets of staggering complexity, worlds threading needles between massive stellar bodies, tracing orbital paths that must avoid catastrophe with every single circuit they make around their twin suns. Think about Earth for just a moment. Our planet orbits one star in a path that's relatively predictable, relatively stable. Ancient astronomers mapped our movements with remarkable accuracy, using nothing but careful observation and mathematics scratched onto clay tablets. The gravitational equation was simple enough to solve with patience and clear skies. Now multiply that complexity. Add a second star to the system. Suddenly the gravitational landscape becomes a shifting terrain of peaks and valleys, stable zones and chaos zones. the planet must navigate between two sources of immense gravity, each pulling on it, each influencing its trajectory. It's not like rolling smoothly along a circular track anymore. It's more like walking a tightrope strung between two swaying towers, where every step requires perfect balance, perfect timing, perfect execution. One misstep and you fall. That HD 143811 ABB exists at all is extraordinary. That it's been stable, that it's been orbiting successfully for what must be millions or billions of years without being flung into space or pulled into one of its stars is almost beyond belief. But here's what makes this discovery even more significant to us, to scientists studying these systems, to anyone trying to understand how common planets really are. This is the closest circumbinary planet system we've ever detected, located approximately 446 light-years from Earth. Not close in the sense that we could visit it with our current technology. We're still talking about distances measured in light-years, distances that would take generations to cross even with spacecraft far more advanced than anything we've built. But close in cosmic terms, close enough that our telescopes can study it in detail, close enough that we can analyze its properties, measure its orbit, begin to understand what kind of world it actually is beneath that designation in our catalogues. And that proximity matters more than you might think, because every detail we gather about HD 143811 ABB teaches us something fundamental about how planets form in the first place, how they survive in extreme environments, what kinds of conditions might exist on worlds utterly unlike our own. For decades we thought planets like this were theoretical curiosities at best, possible in principle but vanishingly rare in practice. The formation environment around binary stars seemed too violent, too chaotic for planets to coalesce. The gravitational forces at play should prevent worlds from forming in the first place, and if somehow a planet did manage to form despite the odds, conventional wisdom said it would be ejected from the system or destroyed within a cosmically short period of time. Yet here it is, stable, orbiting, existing in defiance of what we believed were unbreakable rules. How many other rules are we wrong about? How many other impossible worlds are circling stars we haven't looked at closely enough yet? How much stranger and more diverse is the universe than we've allowed ourselves to imagine? Let's understand what we're really talking about when we say circumbinary planet, because the concept is more remarkable than those two words might suggest. You've spent your entire life on a planet that orbits one star. That's your reference point. That's normal. The sun rises, the sun sets, and the mechanics of that daily rhythm are baked into your biology, your culture, your fundamental sense of how the cosmos works. But a circumbinary planet doesn't orbit one star. It orbits two, and that changes absolutely everything about how that world exists. Imagine standing in the center of a room. In front of you, two people are waltzing together, not in a straight line, but in a circle, spinning around a point between them. That point, the center they're both moving around, is their shared balance point. Now imagine you're trying to walk in a circle around both of them while they dance. You have to constantly adjust your path to account for their movements. When one dancer swings toward you, you have to veer away. When they both move in the same direction, you have to compensate. It's not impossible, but it requires balance, timing, and a stable path that avoids getting caught in the chaos of their motion. That's what HD 143811 ABB is doing on a cosmic scale, except the dancers are stars and the forces involved are so immense they bend space and time itself. The two stars in this system are locked in their own orbital dance, circling their mutual center of gravity, and the planet traces a path around both of them, maintaining a distance that keeps it stable, despite the complex gravitational forces tugging at it from two different massive sources simultaneously. This is extraordinarily difficult. In a single-star system like ours, the gravitational landscape is relatively smooth. The sun dominates everything. Its gravity shapes the orbits of all the planets, and while those planets exert tiny gravitational influences on each other, the sun's overwhelming mass keeps everything predictable and stable over billions of years. In a binary system, no single body dominates in quite the same way. Both stars contribute significant gravitational pull, and because they're moving, because they're constantly orbiting each other, the gravitational field the planet experiences is shifting all the time. Think of it like trying to maintain your balance on a boat in choppy water. On calm seas, it's easy. You barely have to think about staying upright. But when the water is turbulent, when waves are coming from multiple directions at once, you have to constantly adjust your stance, shift your weight, react to forces that change moment by moment. One wrong move and you're over the side. HD 143811, ABB is sailing through gravitational turbulence that would have destroyed a less stable orbit in relatively short order. Yet it endures, it persists, it's found a path through the chaos that works. Think about that. Right now, as you're watching this, that planet is completing another orbit around its twin suns. The same dance it's been performing for 13 million years, since roughly 50 million years after the dinosaurs went extinct. We've only known about it for a few years, but it's been there all along, threading that gravitational needle with perfect precision, orbit after orbit after orbit. So how did it get there? How do circumbinary planets form in the first place when the environment seems so hostile to planetary formation? Planets are born from the disks of gas and dust that surround young stars. In a single star system, that disk spreads out in a relatively smooth flat plane. Particles collide, stick together, gradually building up from microscopic dust grains to pebbles to boulders to mountain-sized objects to planet-sized bodies. It's a slow process, taking millions of years, but it's well understood at this point. We've observed it happening. We've modelled it in our computers. We know how it works. In a binary system, everything is messier. The two stars disrupt the disk with their combined gravity. They can carve gaps in the material, create turbulent zones where particles smash into each other too violently to stick together, heat the disk to temperatures that prevent easy clumping. For a long time, scientists thought this environment was simply too hostile for planets to form. The conditions seemed wrong. The physics seemed to work against planetary formation. But nature, as we keep learning, is more resourceful than we give it credit for. Recent research suggests that circumbinary planets likely form farther out from their stars, in the cooler, calmer regions of the disk where the gravitational turbulence is less intense, where the material has a better chance to settle and coalesce. Out there in those outer regions, dust becomes rock. Rock becomes small planet building blocks, objects miles and miles across. Planetesimals become planets through continued collisions and gravitational accumulation. And then something remarkable happens over immense stretches of time. The planet migrates inward. Gravitational interactions with the remaining disk material, with the stars themselves, with the complex dance of forces in the system, gradually nudge it closer to the centre. It spirals inward, not catastrophically, but slowly, almost gently on cosmic timescales, until it settles into a stable orbit that threads the gravitational needle between its two parent stars. This migration process is incredibly delicate. If the planet moves too fast, it destabilizes and gets ejected. If the timing is wrong, if the disk properties aren't just right, the planet crashes into one of the stars or gets flung out into the cold darkness of interstellar space. But if conditions align perfectly, if the disk properties, the stellar masses, the orbital dynamics all work together in just the right way, the planet finds a stable path. And there it stays for billions of years, circling, surviving, existing against the odds. HD 143811 ABB is proof that this process works in reality, not just in computer simulations. It's proof that planets can form, migrate, and stabilize in environments we once dismissed as impossible. And that has implications far beyond this one system, because if circumbinary planets can exist here, they can exist elsewhere, around other binary systems, around systems with even more complex stellar configurations. The universe is full of multiple star systems. They're actually far more common than single stars like our Sun. If all of those systems have the potential to host planets, then the number of worlds in our galaxy just multiplied dramatically beyond our earlier estimates. We used to think of planets as rare, precious things, special accidents of cosmic chemistry that only happened under very specific, favourable conditions. If you grew up in the 1960s or 70s, that's what science taught us. Earth might be alone or nearly alone in a vast empty cosmos. But the more we look, the more we find planets everywhere we turn our telescopes, around every type of star we can observe, in every kind of system we study. The galaxy is drowning in planets, and HD 143811 ABB is teaching us that even the most extreme environments, places where two stars burn side by side, can cradle worlds. The universe is far stranger and more populated than we ever imagined. Let's talk about what it's actually like on this planet, because that's where things get truly alien, where our Earth-based intuitions completely break down. When we think about habitability, about whether a planet could support life, we talk about the habitable zone. You've probably heard it called the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on the surface. In a single star system, the habitable zone is a ring-shaped region at a certain distance from the star. Move too close and water boils away into steam. Move too far and it freezes into ice. Earth sits comfortably in the Sun's habitable zone, right in that sweet spot. And that's why we have oceans, weather systems, and the entire web of life that depends on liquid water. In a binary system, the habitable zone is more complicated. It's not a simple ring anymore. It's a shifting, dynamic region that depends on the combined heat output of both stars, the distance between them, the way their orbits affect how much energy reaches different parts of the system. HD 143811 ABB orbits outside what we'd traditionally call the habitable zone. This is not a temperate Earth-like world with blue skies and comfortable temperatures where you could walk around in a t-shirt. This is something else entirely, something that operates by different rules. But that doesn't mean it's uninteresting. Far from it. Because even if this world isn't habitable by our standards, by the narrow standards we've developed based on the one planet where we know life exists, it's a laboratory for understanding planetary climates in extreme conditions. It's a place where atmospheric dynamics, heat distribution, and day-night cycles, if you can even call them that, operate under rules we're only beginning to decode, only beginning to simulate in our most sophisticated climate models. And here's something worth considering. Perhaps there are moons orbiting this planet, exomoons, natural satellites that could themselves sit in more favourable temperature zones that could experience different conditions than the gas giant they circle. Perhaps life, if it exists in this system at all, isn't on the planet itself, but on a moon hidden in the data we haven't fully analysed yet, a world we haven't detected yet with our current instruments. That's the thing about discovery. Every answer opens up 10 new questions. Every world we find reminds us how much we still don't know, how much remains to be uncovered. To truly understand HD 143811 ABB, we need to understand the stars it orbits, because those two suns aren't just background scenery in this cosmic drama. They're the architects of the planet's entire existence. They determine its climate, its energy budget, its orbital stability, its very survival. The primary star, the brighter, more massive of the two, is what astronomers classify as an F-type star, slightly hotter and more luminous than our Sun. F-type stars burn hotter than our Sun, hot enough to glow with a bluer, whiter light instead of yellow. They burn brighter with a blue-white tint rather than the yellow we're familiar with. The primary star in the HD 143811 system shares some fundamental characteristics with our Sun: stable hydrogen fusion, middle-aged by stellar standards, but burns hotter and more intensely. If you could somehow stand near it in a hypothetical spacecraft at a safe distance, you'd notice its more intense blue-white glow, fiercer and brighter than our familiar Sun. This star is the dominant partner in the binary system. It contributes most of the total light and heat that the planet receives. If there were only this one star, the system would look almost Earth-like in structure. Predictable, stable, almost boring by comparison to what actually exists. But there isn't only this star, there's a companion, and that companion changes everything about how this system functions. The secondary star is an emma dwarf, what we commonly call a red dwarf. It's smaller and cooler and dimmer than its partner. Dwarfs are actually the most common type of star in our galaxy by far, making up the vast majority of stellar objects. They burn slowly, miserly with their hydrogen fuel, lasting for trillions of years, far longer than the universe has currently existed. They glow deep red, like embers in a dying fire, and they pour out most of their energy in wavelengths our eyes can't see. Infrared light that warms but doesn't illuminate the way visible light does. This secondary star orbits the primary in a cosmic dance, and together they define the gravitational architecture of the entire system, creating the complex environment that the planet must navigate. The two stars complete their mutual orbit approximately every 18 days. The distance between these two stars isn't enormous. In some binary systems, stars orbit each other at vast distances, so far apart that each essentially acts as a single star with its own separate planetary system. But in close binaries like HD 143811, the stars are near enough to each other that they function as a single, complex unit, their gravitational fields overlapping, their light and heat combining in ways that create a unique environment for any circling planets. Imagine standing on HD 143811 ABB's surface. If it even has a surface beneath its thick atmosphere, you look up into the alien sky, you see two suns hanging there. But they're not stationary like our Sun appears to be from Earth's surface. These two suns move relative to each other across the sky. Over the course of days or weeks, depending on the exact orbital mechanics we're still working to refine, they trace paths that bring them closer together and then separate them, creating a dynamic light show unlike anything you could witness anywhere in our solar system. When both stars are on the same side of the sky, positioned close together from the planet's perspective, HD 14311 ABB receives maximum light and heat. This is the system's high noon, a time of intense illumination when the combined output of both stars floods the surface with energy, heating the atmosphere, driving powerful weather systems, creating temperature gradients that would seem extreme by Earth standards. When the stars are on opposite sides of the sky, the light is more diffuse, more balanced. The planet still receives energy from both directions simultaneously, but the intensity is lower, the heating less concentrated. This is the system's equivalent of dusk and dawn occurring at the same time, though that analogy doesn't quite capture the strangeness of what actually happens. And there are moments, rare moments depending on the exact orbital geometry and where the planet is in its own circuit around the stars, when one star eclipses the other from the planet's perspective, when the brighter primary passes in front of the dimmer secondary, or vice versa. During these eclipses, the total light reaching the planet drops noticeably, not into complete darkness, not the way our nighttime works, but into a dimmer state that has no real equivalent in our experience, a shadowed noon, a twilight that shouldn't exist by the rules we learned growing up on Earth. These stellar dynamics create a climate pattern on the planet that's far more complex than anything we experience here. Heat doesn't arrive evenly throughout the planet's day or year. It pulses. It varies depending on where the planet is in its orbit and where the two stars are in their mutual dance. Any atmosphere the planet has, and based on its size and mass we're quite confident it does have a substantial atmosphere, must respond to these variations, expanding when heated, contracting when cooled, generating winds and weather systems driven by temperature gradients that shift on timescales both fast and slow, creating a dynamic atmospheric environment that never quite reaches equilibrium. Stars don't just shine passively into space, they emit stellar wind, streams of tiny charged particles that pour outward at incredible speeds. Our Sun does this, creating what we call the heliosphere, a bubble of solar wind that extends far beyond the planets and protects us from interstellar radiation. In a binary system, you have two stellar winds interacting with each other. Where they meet between the stars, they collide, creating shock fronts, turbulent regions where particles are accelerated to high energies. This interaction zone is magnetically complex, electrically active, and constantly shifting as the stars orbit each other. HD 143811 ABB passes through different regions of this stellar wind environment, depending on where it is in its orbit. Sometimes it's partially shielded from one star's wind by the bulk of the other star and its wind. Sometimes it's exposed to both winds simultaneously, buffeted by particle streams from two different directions. This variable exposure could have profound effects on the planet's atmosphere over time, potentially stripping away lighter elements gradually, or energizing the upper atmosphere in ways that create auroral displays far more intense and extensive than Earth's northern lights, curtains of light rippling across the sky in colors dictated by the atmospheric composition being excited by incoming particles. HD 143811 ABB didn't announce itself to us. It didn't send a signal across the light years. It didn't light up in some obvious way that made astronomers immediately say there's a planet hiding in that system. Finding it required patience, precision, and instruments so sensitive they can detect changes in starlight smaller than you could possibly measure with your eyes, changes that require the most sophisticated detectors humanity has ever built. Let me walk you through how we find planets like this, because the process itself is a kind of detective story, a hunt for evidence so subtle that it takes years of observation and mountains of data to confirm what you're seeing is real and not just instrumental noise or some other phenomenon. HD 143811 ABB was found through direct imaging, actually photographing the planet itself, a much rarer and more challenging technique than most planet discoveries. Direct imaging means astronomers actually captured light coming from the planet itself. This is extraordinarily difficult because planets are millions of times dimmer than their stars. It's like trying to spot a firefly hovering next to a searchlight from hundreds of miles away. To accomplish this, Astronomers use special light-blocking devices that act like holding your hand up to block a bright lamp, revealing the faint glow of planets nearby. HD 43811. ABB is still young and hot from its formation, glowing with heat like embers in a fire. Not visible light our eyes could see, but infrared heat glow that specialized cameras can detect. That faint glow made it just bright enough to photograph using instruments at the Gemini and Keck observatories. But here's what makes this discovery even more impressive. It's not orbiting one star, it's orbiting two. Blocking the glare from two stars simultaneously is exponentially more difficult. The planet was first photographed in 2016, but astronomers needed years to be certain. They watched it move alongside the stars across the sky, like a child walking with their parents, confirming it was truly part of the family. By 2022, after multiple observations from different telescopes, the verdict was unanimous. HD 1436811 ABB is real. And at roughly twice Neptune's distance from our Sun, it's approximately 6 times closer to its twin stars than any other circumbinary planet ever photographed. Photographing the planet told astronomers it existed and where it was. But to know what kind of world this is, rocky like Earth or gaseous like Jupiter, they needed to measure its mass. They did this by watching how the planet's gravity makes the stars wobble ever so slightly, like dancers pulling on each other. By measuring those tiny wobbles, they determined HD 14381 ABD is a substantial world, about 6 times Jupiter's mass. Not a small rocky planet, but a gas giant with a thick atmosphere, complex weather, and its own gravitational domain. The technology that makes all this possible is genuinely staggering when you stop to think about it. Telescopes with mirrors so perfectly smooth that if you scaled them up to the size of a continent, the largest bump would be smaller than a coin. Detectors so sensitive they can count individual particles of light arriving from across the galaxy. Computers processing mountains of information, looking for patterns hidden in what initially appears to be random noise. And it's not just one telescope doing this work in isolation, it's a network of observatories, a global collaboration. Ground-based telescopes scattered across the planet, each taking advantage of their unique location, their specialized instruments, their particular strengths. Space telescopes orbiting above Earth's atmosphere, where the air doesn't blur and distort and shimmer the starlight the way it does from the ground. All of them contributing data, all of them pieces of a larger puzzle that only becomes clear when you put everything together. The discovery of HD 14381 ABB represents the culmination of decades of technological development. Every breakthrough, every small advance in our capabilities, brought us closer to being able to detect a world like this. And when they finally confirmed it was real, astronomers had the same thought. We just found Tatooine. Not the movie version from Star Wars, but something even more remarkable, a real planet with real twin suns out there right now. Luke Skywalker's iconic dual sunset wasn't just science fiction imagination. Nature got there first. So what is this world actually like? What would you experience if you could somehow stand on its surface? If surface is even the right word for what exists beneath the thick atmospheric layers? Let's start with the basics. HD 14381 ABB is larger than Earth, significantly so. Based on direct imaging observations and modelling of the planet's luminosity, astronomers estimate it somewhere between the size of Neptune and Saturn, with a mass of approximately 6 times that of Jupiter. Not a small rocky world like our home planet. Not quite a gas giant like Jupiter either, though it's approaching that scale and shares some characteristics. This size tells us something important right away. HD 14381 AABB almost certainly has a thick atmosphere, possibly even a very deep one with extensive layers of clouds and hazes extending far above whatever solid or liquid core might exist at the centre. Worlds this size don't have the same kind of terrain you'd find on Earth or Mars. There are no mountains to climb, no valleys to explore, no solid ground where you could plant a flag. Instead, what you encounter is atmosphere. Miles and miles of it pressing down with crushing weight, swirling with winds driven by temperature differences in the planet's rotation, layered with different chemical compositions at different altitudes. We don't know exactly what gases make up HD 14381 ABB's atmosphere yet. That requires splitting the planet's light into a rainbow of colours, where each gas leaves its own unique signature, like a fingerprint. That kind of detailed observation is at the very edge of what our current technology can accomplish for a planet at this distance. But we can make educated guesses based on the planet's size, its mass, and the amount of heat it receives from its twin stars. There's almost certainly hydrogen and helium, the most abundant elements in the universe, and the primary components of gas giant atmospheres throughout our galaxy. There might be methane, ammonia, water vapour in various concentrations, perhaps more complex organic molecules formed when starlight breaks apart simpler molecules like breaking apart Lego bricks, then allowing them to snap together in new combinations, building up a chemical inventory that could be surprisingly diverse. If the planet formed farther out in the system and migrated inward over time, as circumbinary planets are thought to do, then it might have an atmosphere enriched with materials from the outer system, frozen gases and ices that turned to vapour as the planet moved closer to its stars, adding water and other compounds to the atmospheric mix. The atmosphere might have clouds, but not the fluffy white water clouds we see on Earth. These could be clouds of methane or ammonia, clouds of more exotic compounds we don't encounter in our everyday experience. These clouds could form bands like the stripes on Jupiter, circling the planet in zones shaped by heat rising and the planet's spin. And the colours would be utterly unearthly. On Earth, our sky is blue because of the way sunlight scatters through nitrogen and oxygen molecules. On HD 143811 ABB, with a completely different atmospheric composition, with light from two stars arriving at different angles and different intensities throughout the planet's orbit, the sky might be shades we don't have proper words for. Deep ambers, burnt oranges, perhaps greenish tinges from methane absorption, perhaps hazes that diffuse the starlight into a perpetual glowing twilight in certain atmospheric layers. Let's talk about the heat, about the energy budget of this world. HD 143811 ABB isn't close enough to its stars to be a scorched, molten hellscape like some of the extreme hot Jupiters we've discovered, but it's not far enough out to be frozen solid either. Not a cold ice world in the outer reaches of the system. It sits in a middle zone, receiving enough energy to maintain relatively high temperatures, but not so much that everything vaporizes. The exact temperature at any given time depends on numerous factors: the planet's distance from the stars during different points in its orbit, how much heat the atmosphere traps through greenhouse effects, how reflective the cloud layers are, how efficiently the planet redistributes heat from one region to another. On Earth we have a simple day side and night side. The sun heats one hemisphere while the other is in darkness and gradually cools. Heat flows from warm regions to cool regions, creating wind, weather patterns, ocean currents, all the dynamics that shape our climate and make Earth the complex system it is. On HD 143811 ABB, the situation is far more intricate. Because there are two stars, the dayside concept gets blurred into something much stranger. Depending on the planet's position in its orbit and where the stars are relative to each other, there might be times when both stars illuminate the same hemisphere simultaneously, creating an intense heating period that drives powerful atmospheric circulation. And there might be times when the stars are positioned on opposite sides of the planet, providing more diffuse balanced heating that creates entirely different weather patterns. This creates climate variations we simply don't experience on Earth, cycles we don't have intuitive understanding of. Not just daily cycles, but longer cycles tied to the orbital mechanics of the binary stars themselves. Periods of intense heat alternating with relatively cooler periods, atmospheric circulation patterns responding to these variations, generating winds that shift direction and strength based on where the dominant heating is coming from at any given time. If you were somehow in the upper atmosphere of HD 143811 ABB, riding those wind currents in a hypothetical observation platform, you'd experience a constantly changing environment. Not chaotic exactly, but rhythmic in a way that's profoundly foreign to everything we know from living on Earth. Now we should be clear about something. HD 143811 ABB is almost certainly not habitable for life as we know it. The temperatures are likely too high, the atmospheric pressure too extreme, the chemistry too different from what Earth biology requires. There's no solid ground to stand on, no liquid water in stable surface pools. But habitable is a narrow definition based on one type of chemistry, one solution to the problem of self-replicating systems that we happen to have studied in detail because it's the only example we have. Could there be life on HD 143811 ABB? Life that evolved under these specific conditions, adapted to high temperatures and thick atmospheres and variable stellar input? Life that floats in the air currents, metabolizing compounds we wouldn't think of as food, reproducing in ways we haven't imagined because we've never encountered them. We don't know. We have no evidence one way or the other at this point. But the question is worth asking, because if life can exist in Earth's deep oceans, in acidic hot springs, in frozen Antarctic lakes sealed under ice, in solid rock miles below the surface, then perhaps it can exist in environments that seem completely alien to us. And even if HD 43811 ABB itself is lifeless, that doesn't necessarily mean the entire system is devoid of life. Because planets aren't the only places where life might take hold. What if this gas giant has moons? Large planets in our own solar system have extensive moon systems. Jupiter has dozens of confirmed moons. Saturn has dozens more. Some of those moons are geologically active worlds with subsurface oceans, with chemical processes that might support life in environments completely cut off from direct sunlight. If HD 143811 AB has moons, and statistically there's a reasonable chance it might, then those moons are orbiting in the planet's shadow part of the time, periodically shielded from the direct heat and radiation of the twin stars. They might have different temperature regimes, different atmospheric conditions. They might have solid surfaces, atmospheres of their own, conditions that are more temperate, more Earth-like in some ways than the gas giant they orbit. We don't have the observational resolution yet to detect moons around HD 143811 ABB. That's the next challenge facing astronomers, the next layer of discovery waiting for improved instruments and techniques. But it's plausible, it's possible, and that possibility adds yet another dimension to an already extraordinary system. So why does HD 1.381 ABB matter so much? Why should you care about a gas giant orbiting two stars dozens of light years away, a place you'll never visit, a world that's hostile to everything you recognize as alive? The answer cuts to the heart of why we explore, why we study distant worlds, why we invest resources in understanding places we can never touch. Every time we find a planet that shouldn't exist according to our old models, according to the theories we developed based on limited data, we're forced to revise those models. We're forced to expand our understanding, and that expansion has ripple effects across everything we think we know about planets, stars, solar system formation, and ultimately the potential for life beyond Earth. For most of human history, we didn't know planets existed outside our own solar system. We suspected, we theorized, but we had no proof, no way to confirm our speculations, and when we finally started detecting exoplanets in the early days of that search, what we found shocked the astronomical community. Hot Jupiters, massive gas giants orbiting insanely close to their stars, completing orbits in just a few days. These planets shouldn't have been there according to our formation theories. Gas giants should form far from their stars where it's cold enough for ice to condense and build up massive planetary cores. Yet there they were, scorched and bloated, whipping around their stars in impossibly tight orbits that violated everything we thought we understood. That discovery forced scientists to develop entirely new theories. Migration theory, the idea that planets can form in one location and move to another over time. The understanding that planetary systems aren't static snapshots but dynamic, evolving environments where gravitational interactions shuffle worlds into new configurations over millions of years. HD 143811 ABB is another one of those paradigm-shifting discoveries, another reminder that we need to remain humble about what we think is possible, because not only is it a planet in a binary system, something we thought was rare or maybe impossible, it's also close enough for us to study in meaningful detail, and that proximity means we can test our theories rigorously, refine our models based on actual observations rather than speculation, push our understanding forward based on evidence. Here's what this discovery teaches us about the universe we inhabit. First, planetary formation is more robust than we thought. The process of building planets from dust and gas isn't fragile or finicky. It doesn't require perfect conditions in a perfectly quiet environment. It can happen in chaotic places, around multiple stars. In systems where gravitational forces are tugging in multiple directions simultaneously, where everything seems to work against the slow accumulation of material into coherent worlds. That means planets are common throughout the galaxy, not just around single sun-like stars in quiet, stable systems, but everywhere we look. Around binaries, around red dwarfs, around massive stars, around old stars in dense clusters where gravitational interactions between stars are frequent. If planets can form anywhere, then our galaxy is teeming with them beyond our ability to count or catalogue. Trillions of worlds, more planets than stars, more environments than we can imagine exploring. Second, the habitable zone concept needs to be fundamentally rethought. We've been using the habitable zone as a shortcut, a simple way to identify which planets might support life based on temperature alone. But the habitable zone was developed for single-star systems. It's a ring at a certain distance where liquid water can exist on a planet's surface based on simple energy balance calculations. In a binary system, the habitable zone moves over time. It shifts as the stars orbit each other, as the amount of combined energy reaching any given distance changes throughout the orbital cycle. A planet that's in the habitable zone at one point might drift out of it later, only to return. That creates complex climate cycles, freeze-thaw cycles, periods of warmth followed by cold that could actually have interesting effects on the development and evolution of any potential life, forcing organisms to adapt to changing conditions rather than stable equilibrium. But it also means the habitable zone isn't a death sentence if you're outside it. A planet with a thick atmosphere can trap heat effectively, maintaining warm conditions even at greater distances through greenhouse effects. A planet with tidal heating, internal heat generated by gravitational flexing from being in a complex orbital environment, can stay warm without relying primarily on starlight. And then there are those moons we keep coming back to. Moons orbiting gas giants in circumbinary systems might experience entirely different conditions than the planets they orbit, heated by tidal forces, potentially harbouring subsurface oceans, maintaining temperate conditions through mechanisms that have nothing to do with simple distance from the stars. HD 143811 ABB is teaching us that habitability is more complex, more nuanced, more multifaceted than a simple calculation based on distance and stellar luminosity. It's teaching us to think about planetary systems as interconnected webs of possibilities, rather than isolated objects that either are or aren't habitable based on a single criterion. And third, perhaps most importantly, we need to maintain humility about what we think we know. Every time we set firm boundaries, every time we say planets can't form here or life can't exist there, the universe proves us wrong. Nature is more creative than our theories. Reality is stranger and more diverse than our models, which are always simplifications, always based on incomplete information. Circumbinary planets were dismissed for decades as too hard to form, too unstable to survive. And yet here they are. Not just HD 143811 AB, but dozens of others we've found in recent years. Each one a reminder that the universe doesn't care what we think is impossible, doesn't read our textbooks or follow our predictions. It simply is, following the laws of physics wherever they lead. HD 143811 ABB is not alone in the universe. It's part of a growing family of circumbinary planets, worlds orbiting binary star systems that we've discovered over the past decade and a half. And each one has its own story, its own unique characteristics, its own lessons to teach. Together they're painting a picture of just how common and diverse these systems really are. How many variations on the theme exist out there in the darkness. The first confirmed circumbinary planet was Kepler 16b, discovered back in early years of exoplanet detection. That discovery made headlines around the world because it was the first unambiguous detection of a planet orbiting two stars simultaneously. Astronomers nicknamed it Tatooine almost immediately. The Star Wars reference was too perfect to resist, too embedded in popular culture to ignore. Kepler 16b orbits a pair of stars smaller and cooler than our Sun. It's about Saturn's size, cold and distant from its stars, almost certainly lifeless. But its discovery was absolutely monumental because it proved circumbinary. Planets weren't just theoretical constructs. They were real. They existed out there. And if one existed, basic statistics suggested there would be others. And there were. The list grew rapidly as astronomers analysed data from the Kepler Space Telescope, which spent years staring at the same patch of sky, monitoring the brightness of thousands of stars simultaneously looking for the telltale dips of transiting planets. Each new discovery refined our understanding, added nuance to our models. Some of these planets were massive gas giants. Others were smaller, closer to Neptune's size. Some orbited close to their stars at distances similar to Earth's orbit around the Sun. Others were farther out in colder regions of their systems. What they all had in common was the remarkable fact that they existed at all despite our earlier skepticism. Circumbinary planets weren't vanishingly rare as we'd assumed. They were uncommon, yes, but not impossibly so. Current estimates suggest somewhere between 5 and 10% of binary systems might host planets. That might not sound like a lot, but when you consider how many binary systems exist in our galaxy alone, it translates to billions of circumbinary worlds, billions of places where twin suns rise over alien horizons. What makes HD 133S811 AB B particularly special among this growing family? The answer is proximity. HD ABB is the closest circumbinary planet system discovered to date. It's close enough that our telescopes can study it in far greater detail than more distant systems. Close enough that future observatories will be able to analyze its atmosphere carefully, measure properties we can't access with current technology, detect moons if they exist and are large enough. Most of the circumbinary planets we've found are hundreds or even thousands of light years away. That distance makes detailed study challenging. We can detect them, measure their basic orbital and physical properties, but we can't yet probe them deeply, can't yet answer the detailed questions we'd like to ask. HD 133S811 ABB changes that equation. Its relative proximity makes it a prime target for intensive study over the coming years and decades. It's our best chance in the near term to really understand what circumbinary planets are like beyond the basic statistics, to characterize them as complex worlds rather than just data points in a catalogue. So where do we go from here? What's the next chapter in the story of HD 133S811 ABB and worlds like it scattered throughout the galaxy? The answer is deeper, more detailed, more ambitious, because discovering this planet is just the beginning, just confirming it exists. Now that we know it's there, now that we have its orbital parameters and basic properties, we can point our most powerful instruments at it and start asking more sophisticated questions, questions that get at what this world is really like. First on the agenda is atmospheric characterization. Right now we know HD 133S811 ABB exists. We know its size, its mass, its orbital period. But we don't yet know what its atmosphere is composed of, whether it has clouds or hazes, what complex chemistry might be happening in its upper layers. To answer those questions we need spectroscopy, splitting the planet's light into its component wavelengths and looking for the absorption signatures of specific molecules. When starlight passes through a planet's atmosphere during a transit, certain wavelengths get absorbed by whatever gases are present. By measuring precisely which wavelengths are absorbed, and by how much, we can identify those gases and even estimate their abundances. This technique has already been used successfully on other exoplanets. We've detected water vapor, methane, carbon dioxide, sodium, even more exotic compounds on distant worlds. But it requires extremely sensitive instruments, long observation times, and painstaking data analysis to tease the planetary signal out of all the noise and confounding factors. HD 133S811 ABB is a prime target for this kind of study, because its proximity means the signal will be stronger than for more distant planets, and its substantial size means it has a thick atmosphere to probe. The James Webb Space Telescope, which revolutionized astronomy, with its unprecedented infrared capabilities, is one of the instruments that could study HD 133S811 ABB this way. Webb is designed specifically for infrared spectroscopy, perfect for analyzing exoplanet atmospheres that emit and absorb primarily in infrared wavelengths. As its mission progresses and observation time gets allocated to various targets, HD 133S811 ABB will likely be added to the schedule. What will we find when we finally get that data? We don't know, and that's what makes it exciting. Maybe water vapor in significant quantities. Maybe methane indicating active chemistry. Maybe something completely unexpected, a compound we didn't anticipate, a signature that tells us the planet's chemistry is different from what our models predicted. Every answer will raise new questions. That's how science works, how knowledge grows, how we push the boundaries of understanding forward one observation at a time. Second, there's the tantalizing possibility of searching for moons orbiting this gas giant. We've talked about how large planets in our solar system have extensive moon systems, so it's entirely reasonable to assume exoplanets do as well. But detecting exomoons is incredibly difficult. Moons are small, their gravitational effects are tiny. The signals they produce, whether through subtle transit timing variations or other indirect methods, are buried deep in observational noise. Still, astronomers are developing techniques specifically aimed at finding exomoons. They're looking for subtle variations in transit timing caused by the gravitational tug of a moon pulling the planet slightly ahead of or behind its expected position. They're searching for secondary transits, additional tiny dips in brightness, when a large moon crosses in front of the star separately from the planet. No exomoon has been confirmed with absolute certainty yet, though there are tantalizing candidates under investigation. HD 143811 ABB, because of its size and our ability to observe it repeatedly, is an excellent place to search for these elusive natural satellites. If we find a moon there, if we confirm HD 143811 ABB has natural satellites, that discovery will open yet another entire avenue of investigation. What are those moons like? Are they icy worlds? Rocky bodies? Do they have atmospheres of their own? Could any of them be habitable despite orbiting a planet that itself isn't suitable for life as we know it? The questions multiply exponentially with each new discovery. Third, long-term monitoring of this system over years and decades will reveal whether the planet's orbit is perfectly stable, or whether there are subtle perturbations caused by unseen planets or other factors in the system. It will allow us to track atmospheric variations over time, looking for seasonal patterns or responses to stellar activity, flares and variations in the star's output. This kind of patient long-term study requires coordinated observation campaigns, careful data management, and sustained commitment across generations of astronomers. But the payoff is a much richer understanding of the system as a dynamic evolving entity rather than a static snapshot frozen in time. And looking farther into the future, more speculatively, might we someday send a probe to HD 143811 ABB? Right now, that's firmly in the realm of science fiction. The distances are immense, the technological challenges overwhelming. Even our fastest spacecraft would take tens of thousands of years to reach systems dozens of light years away. We don't have the technology for practical interstellar travel, and we're nowhere close to developing it. But that doesn't mean it's impossible forever. Concepts like laser-pushed light sails could potentially accelerate small probes to significant fractions of light speed, making journeys to nearby star systems possible within human lifetimes, or at least within reasonable mission durations. Would such an ambitious mission be worthwhile? That depends entirely on what we learn in the meantime through our telescopic observations. If atmospheric studies reveal something extraordinary, if we find biosignatures or complex organic chemistry, or evidence of habitable moons, then the case for sending a physical probe becomes far more compelling. Let's step back from the technical details for a moment and think about what all of this really means, what it says about us and our place in this vast cosmos. HD 143811 ABB is a planet, a massive ball of gas held together by gravity, circling two stars in a distant corner of the galaxy. It has no awareness of us. It doesn't know we exist. It doesn't care that we've detected it, measured it, studied it from across the light years, and yet for us, for humanity, it matters profoundly. Because finding this planet is more than just adding an entry to a catalogue or publishing a paper in a scientific journal. It's an act of reaching out beyond ourselves, beyond the familiar, beyond the comfortable boundaries of our home world. It's proof that we can understand things we cannot touch, places we cannot visit, phenomena that exist entirely outside the realm of our direct sensory experience. Think about the audacity of that for a moment. We've never been to HD 143811 ABB. No human will go there in our lifetimes, in the lifetimes of our children, probably not for many generations if ever. The distances are too vast, the challenges too great. But we know it's there. We know what it orbits. We know its size, its mass, its year, its basic properties. We've reached across dozens of light years with nothing but instruments and mathematics, and we've touched that world with our minds. That's extraordinary. That's a kind of magic that would have seemed impossible to our ancestors just a few generations ago. And yet it's real. It's happening right now. It's what we as a species have learned to do. For most of human history, we thought Earth was the center of everything. The stars were lights on a celestial dome above us. The planets were mysterious wanderers. The universe was small, comprehensible, centered on humanity and our concerns. And then slowly, painfully, we learned otherwise. Earth orbits the Sun. The Sun is one star among hundreds of billions. Our galaxy is one galaxy among trillions. The universe is so vast that light from the most distant galaxies takes billions of years to reach us. meaning we see them not as they are now, but as they were when the universe itself was young. Every step of that journey, every discovery that expanded our cosmic perspective, met resistance at first. People didn't want to believe Earth wasn't special, wasn't the centre. They didn't want to accept that we're on a small planet orbiting an ordinary star in an unremarkable part of a typical galaxy. But the evidence was undeniable. The mathematics worked. The observations confirmed it again and again, and eventually we accepted the truth. We're not the centre of the universe. We're not special by virtue of our location in space. And yet that realization didn't diminish us. It elevated us in a different way. Because if we're not special by location, we're special by awareness, by consciousness, by curiosity, by the fact that we can look out into the vastness, recognize our cosmic insignificance, and still persist in trying to understand everything we can reach with our instruments and our minds. HD 1433811 ABB is part of that understanding. It's one more piece of the cosmic puzzle we're slowly assembling. One more answer to the eternal question that's driven exploration throughout human history. What's out there? And what's out there, we're learning with each new discovery, is more diverse, more strange, more beautiful than we dared imagine. Planets around single stars, planets around binary stars, planets around the remnants of dead stars, rogue planets drifting through the darkness between stars, worlds of fire and ice, worlds covered in oceans or wrapped in clouds, worlds so alien they challenge our ability to imagine what standing on their surfaces would be like. Every kind of place we can conceive, and many we couldn't conceive until we found them and they forced us to expand our conceptual boundaries. And every one of those places is real. They exist right now. Orbiting their stars or drifting through space, following the laws of physics, existing whether we observe them or not. But we do observe them. We've developed the tools, the techniques, the mathematical frameworks to find them, to study them, to begin understanding them. And that matters. It matters because knowledge itself is valuable. Understanding is precious. The long, slow accumulation of wisdom about the universe we inhabit is perhaps the most fundamentally human project there is. We may never set foot on HD 1433811 ABB, but our descendants might set foot on worlds like it. Generations from now, if we survive as a species, if we continue growing and developing and pushing our technological capabilities forward, humans might visit circumbinary planets. They might stand in the light of twin suns and remember that people centuries earlier detected those suns from across the galaxy with nothing but patient observation and careful thought. Or maybe we'll never travel there physically. Maybe the distances really are too great to overcome practically. But even then we'll continue learning. We'll continue observing, analysing, understanding, expanding the map of the known, filling in details, answering questions, discovering new mysteries that we couldn't have asked before because we didn't know enough. Because that's what we do. That's what defines us as human. Curiosity isn't just a side effect of intelligence. It's the core of it, the driving force. It's what pushes us to look beyond the horizon, to ask what if, to seek answers even when the questions are difficult and the answers are slow in coming. HD 1433811 ABB is an invitation from the universe. It's reality saying, here, look at this. It's stranger than you thought, more complex than you predicted, but you can understand it if you try, if you're patient, if you're willing to revise your assumptions when the evidence demands it. And we are trying, every single day. Every observation from telescopes around the world and in space, every analysis running on computers, every paper published, every student inspired to study astronomy, every person who looks up at the night sky and wonders what's really out there beyond the tiny points of light visible to the naked eye. That's the legacy of discoveries like this. They don't just add to scientific knowledge in some abstract academic way. They add to human wonder. They remind us that there's still so much to learn, so many questions left unanswered, so many frontiers still unexplored, even in an age where the Earth itself feels completely mapped and known. The universe offers endless new frontiers, endless places we haven't been, endless mysteries we haven't solved. HD 1433811 ABB is one of those mysteries in the process of being solved, not a complete mystery anymore, but still mysterious in its details, still waiting to reveal its full story as our instruments improve and our understanding deepens. So when you hear about HD 1433811 ABB, don't just think of it as a distant planet that has nothing to do with your life. Think of it as a testament to human curiosity, to ingenuity, to the relentless drive to know more, understand better, see farther than the generation before. Think of it as a reminder that we're part of something larger than ourselves, larger than our daily concerns, larger than our brief individual lifetimes, part of a universe that's been unfolding for billions of years and will continue for billions more, part of a cosmic story that includes stars and planets and galaxies, and also includes us, watching, learning, marveling at the sheer scope of what exists. And think of it as an invitation to keep looking up, to keep asking questions, to stay curious about the universe we inhabit. Because there are more discoveries coming, more planets waiting to be found, more systems that will challenge our assumptions, more strange and wonderful configurations that will expand our understanding of what's possible, and you get to witness it. You get to be here now during this extraordinary time in human history when we're finally learning what's really out there beyond our small corner of space, when the universe is revealing its secrets to those patient enough and clever enough to listen. That's not a small thing. That's not something to take for granted in the noise and distraction of daily life. Look up, wonder, ask questions, follow the discoveries as they unfold in the news, in scientific journals, in documentaries and articles, and remember, somewhere out there, dozens of light years away, a planet circles two suns. It exists. It's real. It's there right now, following its orbit, experiencing its twin sunrises, existing in defiance of what we once thought was impossible. We found it by looking, by building instruments, by doing the mathematics, by refusing to accept that some things are unknowable. We found it, and that means we can find more, we can learn more, we can understand more about this cosmos we're privileged to inhabit. That's the journey. That's the adventure humanity is on. And HD 143811 ABB, this impossible planet with its twin suns, is one remarkable stop along the way.